Implicit differentiation is a different way to look at finding the derivative of functions, especially for non-functions. Okay, so let's look at this question first. What if I asked you to find the derivative of xy equals 1? So to be able to find this derivative like we have been doing, we would have to solve it for y first. So we divide by x, and y would equal 1 over x. So to find that derivative, which I'm going to write as dy dx, we would take the power rule there because this is x to the negative 1. And then we would get negative 1 over x to the second power once you subtract and simplify. Okay, so if we're given a function, that's a function of x, we can solve it for y and take the derivative. However, not all functions are what we call explicit, which can be solved for y. An implicit function is not one in which there is one value of x for every y, but it still can be derived. For example, a circle. Our circle standard equation here is x squared plus y squared equals whatever number squared, okay? Now we have an x and a y here, so we haven't really learned how to find that derivative without having to solve for y. Okay, so we're going to learn that today. When taking the derivative of an implicit function, you must take the derivative with respect to x. Okay, so this is notated as d over dx, which we're going to say as derivative with respect to x. Okay, that's important here for implicit. Whenever you see a y, the derivative with respect to x is dy dx. So you will have to add that on, dy dx, whenever you have a derivative of y. And it may take a couple examples to kind of get this, all right? So when we take derivatives with respect to x, you're going to use the rules as you would normally with power, chain product, and quotient for all of your x's. And whenever you have a y, you need to do a chain rule and write the derivative dy dx. Okay, so I'll show you an example here. Example 1, if I wanted to find the derivative with respect to x of x to the third power, so these variables match up. So all I'm really doing is taking the derivative of x to the third, which would be 3x squared. That's your answer there, okay? But when your variables don't match, you end up having a y and you have to take the chain rule. Okay, so these variables don't match. Okay, so if we did this derivative with respect to x, we'd have 3y squared, and then what's the inside function here? Y, and that derivative with respect to x is dy dx. Okay, so we would say 3y squared dy dx for this derivative with respect to x. Okay, so basically if your variables are matching up, then you're good. You just take your derivative. If they're not, so if in this case we have a y, we've got to add in that dy dx because that's the derivative of y with respect to x. Okay, so you kind of just add it on there. So anytime there's a y, you're really just putting in dy dx is really the easiest way to think about it. Because if my variables are matching up, then I'm good. I just take the derivative, okay? So the derivative of x plus 3y with respect to x would just be, so the derivative of x is 1, okay, and then we'll copy the plus, and the derivative of 3y is 3 dy dx, okay? So let me go over that again. This would be the same thing as taking the derivative with respect to x plus the derivative with respect to 3y, okay? So the derivative of x is 1, and the derivative of 3y would be 3, okay? It would just be 3. The derivative of 3y would just be 3. But y doesn't match up with x. Those aren't the same variable. So we've got to put in the dy dx there because that's the derivative of y with respect to x. Here, we don't need to say an x. I mean, if we did, look what would happen. We'd have dx over dx, and that would be 1, right? So that would just go away. Okay, this is your final answer here. 1 plus 3 dy dx. All right? So again, if I have an x and I just put it in the, with respect to x in the same way, it would just cancel out. Okay, so you really just have to worry about it when you have a y. Okay, so this function is a product rule. I have x and then I have y squared. So I've got to do front d back plus back d front. Okay, front d back plus back d front. All right, so my front function is x times the derivative of back. That would be 2y dy dx, okay? Plus back, so y squared, times the derivative of the front. Derivative of x is just 1, okay? So again, we have x's and y's here, which we haven't really done yet. So we have two kind of functions going on. I need to take the derivative, or excuse me, I need to write the front, that's my x, times the derivative of the back. And the derivative of y squared is 2y, but then with respect to x, I need to add that dy dx in, okay? That's my front d back. Okay, plus back is y squared, and derivative of x is just 1. Okay, so let's simplify here. I'd have 2yx dy dx plus y squared. That would be my derivative with respect to x. Okay? All right, C, derivative with respect to x here. This is the same thing as d over dx of 4x to the third minus d over dx of 2y squared, okay? So we're taking the derivative separately, put a minus in between. All right, so let me show you this again. The derivative of 4x to the third would be 12x to the 3 minus 1 squared. And then we're talking about variable x, so it would be dx dx, okay? That's going to cancel out, so we're not going to have that because dx over dx is 1, right? Minus, so we'll do 2y squared. That would be 4y to the 2 minus 1 dy dx. So the variable we derived is y. That needs to go here, okay? That's going to cancel. And we get 12x squared minus 4y dy dx. That's our derivative with respect to x. Okay? So it's kind of taking like a partial derivative, a derivative by variable, if you want to think of it that way. All right, that's it for page 1.